Alright, so let's go ahead. So we have Ankit Barik here today. He's from Joyce Office. So Ankit did his masters from IIT Kharagpur and then his PhD from Max Planck Institute for Solar System Research. Um, he contributed to development of the magic code, which some of you are aware of. It's sort of the widely used code for doing dynamic equations, studying convection in planets and stars. Particularly, I think used widely by in planets by him. Um, when he moved to Johns Hopkins as a postdoc, where he worked with studying beginning, and now he's since the places there. Given that we have a lot of interest in magnetic fields, not just primarily in stars, but now we're developing these interesting planets, with people like Shakshi who are working on star interactions. We'd also like to develop some collaborations with them moving into the future, not just for planetary dynamos, but also stellar dynamos, which we were talking about some time back. Pleasure to have Ankit here, and hopefully we will get to see him more often in the future. So, welcome.
Thank you for the nice introduction and also the opportunity to give a talk here. I'll be talking about stably stratified layers in planets and stars, which are pretty common to see. I'm a developer of a few different codes. The first one is Magic, which I've been involved with the most. Recently, I got involved more with this code called coding, which is modern that can compute eigenmodes of the Stokes equation, induction equation, thermal equation, and so on. And lastly, I worked a bit on this beast of a code called Camera, which is an amazing meter-scale code, which I worked towards adapting to applications towards Numerical. These are my collaborators while working on stable layers of planets and stars. Kimi Moore was a member of the Juno mission with lots of experience on Jupiter data and was a postdoc at Caltech, who we did a lot of Jupiter simulations. Chiyan, postdoc in our group, and has extensive experience with stable layers in Earth and Saturn. Hashem is a PhD at CESSI who I during the summer school of international physics. So he is biologist with also experience in planetary dynamos. And finally, Chris Markovich he does ring seismology design, where you can look at oscillations in Saturnian rings, and then you can infer what the interior structure of the planet is. Very similar to taking out from helioseismology and looking at basically genomes in there. So let me jump right into it. Stably stratified layers, in particular, were cases where they are overlaying layers are quite ubiquitous everywhere. Loads of planets supposedly have them, and massive stars we know there's the thin convections of both like big gray cell, which is stably stratified. So basically, when you have convection, you have hot fluid underneath, cold fluid above, and it overturns. And above that, you have cold fluid below, hot fluid above, so it's very stable towards any overturning. There are several effects of these stratified layers. The most significant one in planetary context is the magnetic filtering through electromagnetic skin, because we have conducting layers really not putting as much in terms of flows. It's not linear, but it's if you have a fast variation in the magnetic field. And this is involved principally to explain the anomalous magnetic field of Saturn, which is a very weak, very high, almost aligned with the rotation axis. And the idea is that you may have very complex inside, but all that is allowed to come out after you have filtered through the stable stratified layer is just a typo. This is also in water just in Mercury field, which is also highly diluted for Ganymede and also for Jupiter. And stable stratified layers can go through ways. So you convective fluence, so the interface, which leads to the generation of waves in the stratified layer. In the case of Earth, for example, these waves are typically in the form of what are known as MAC waves or magnetic Archimedes Coriolis waves. These are the three external forces. And you can observe these waves even in genuine observations. So the idea is that things stable stratified layer of CPS4 and convective fluence lead to the generation of waves in this layer, and you can observe them in geometric observations.
Okay, so just a question, just for the sake of everybody, the definition of safely stratified layer, so you imply it is establishing stratified, but it's not unstable convection, correct? Or,
It is stable convection.
so there is temperature gradient and there is convection going on.
There's convection going on underneath here. Above the, so the temperature gradient is unstable to convection here, but stable to convection.
Right. So basically, then the definition for safely stratified layer is that the temperature gradient is subcritical to first cell gradient. So there is no convection. Last cell pools are absent, although the layer is not happening.
Yes.
Okay. So the dynamics in the unstable layer, and then there is kind of boundary effect because of the safely stratified.
Yes. And you can also have internal radical waves, which are the most common types of waves in stably stratified layers. And I think the letters are a bit blurred here, but in the atmosphere, they give rise to strong zonal waves, so they can effectively, they sort of they break in a similar way that waves on the sea break and give rise to saline flows. You can have something similar happening in the give rise to something called the quasi-biennial oscillation in the Earth's atmosphere. And these sort of effects have been studied in the context of massive stars, where the internal gravity waves are thought to be that they may, they also maybe they can interact with each other and transport energy movement. And finally, stably stratified layers themselves can be opposed to all sorts of different instabilities, both in the hydrodynamic case as well as in terms of energy. Coming back to what this talk is going to be about, so I'm going to talk about three sort of case studies when it comes to stably stratified layer. I'm going to talk about convective layer. Two will involve the gas giants, Jupiter and Saturn, and the third one will massive stars, three solar mass stars, with a convective layer inside a massive radiating. How do we simulate these bodies? We use the elastic approximation, which means that we filter out some waves because we think on the dynamic timescales of convection and animals, they are probably not important to the timescales are too short. So in that case, the mass conservation just reduces to this equation. The evidence of rho u is 0, and rho is the one dimensional mean density. So this is what we call the background density, which means that we stay behind into our simulation and we store all the equations around it. So the set of equations look like that. And all these quantities, the tilde on top, which are colored right here, they all have 1D fixed products throughout simulation. So rho is density, T is the temperature, G is gravity, lambda is magnetic diffusivity. And these 1D models can be obtained either from thermal evolution models or from ab initio calculations, hybrid experiments, and so on. And then you have a set of control parameters, which are non-potential numbers, but Clayton axes love these. And there are four non-potential numbers which control the system. First is the Ekman, this is the Ekman number, magnetic Prandtl number, Wheeler number, and the Prandtl. And you can see this with the initial equations, mass conservation, non-monopoles, maybe Stokes induction equation, and the energy equation.
What is the last terminal? What is S? Right?
Oh, that's a stress tensor.
That's where this is the carrier.
Yes. So these are the four control parameters. It's supposed to indicate the Ekman number, and this is the ratio of the viscous force to the Coriolis force. So the lower the Ekman number, the less viscosity and faster your rotation. And its equations are typically go up to 10 to the power -6, but for actual physical objects, we are obviously many shapes away. So 10 raised to the -15 or so. Next comes the Rayleigh number, which will quantify the thermal driving. So how heavy is the thermal in the system, or how vigorous the convection is. And for simulation, typically go up to around 10 raised to the 10 or so, but for physical objects, this is obviously much higher. And then comes Prandtl number, which is the ratio of viscosity to thermal diffusivity, which will typically be fixed to 1. But in actual astrophysical objects, it can take very little values, which is molecular values. The idea of linear model is basically this idea that Cherry has homogenizes everything when it comes to diffusivities. And then we have the magnetic Prandtl number, which is the ratio of viscosity to magnetic diffusivity. And you can think of it as a measure of the conductivity of the fluid involved.
First number is Ekman number?
Yes, I thought K.
So the problem here is the computational cost, right? I mean, in terms of matching the realistic values of physical objects.
That and also memory.
Memory in what sense?
So the lower you go in Ekman number, the thinner the boundary layers become.
I mean, so you have to have hybrid cards.
Yes.
And so what you mean storing the data for your
So-
time advancing. So
So-
that's where the memory costs are.
So at some point it takes up so much memory that there's no computer on the world that can store it.
Hmm. So is it true for us directly like that that you are not even close to matching those numbers for it's on I understand it's very difficult. But even for art, it's difficult.
Yes.
But do you do some convergence kind of stuff where you slowly increase those numbers and see how things change and do things change when drastically?
So that's what people have been doing in the past year, for example. People have come down to 10 to the power -7 and -8.
Mm-hmm.
And around those numbers, -6 below, you start seeing sort of similar kind of physics. And it resembles more and more the force balance and so on, start resembling more and more what people think the Earth should have. So in terms of the numerical method, we expand the vectors. So our momentum and magnetic field in terms of toroidal and toroidal potentials, which gives us, instead of 3 continuous, you get 2 scalars. And in the process, we used 2 equations, these 2. So these automatically satisfy homogeneous free curvature intervals. Divergence of curves over 0. And then all the scalars are expanded in angles, and they're expanded in terms of spherical harmonics. And then radius are expanded in Chebyshev polynomials. And then you equally end up solving for these coefficients. And then you reconstruct a solution back. The grid looks like that. So typically in radius, the grid consists of zeros of the shift program. The advantage of that is the grid paths, as you can see, start to concentrate closer to the boundaries. And you start resolving boundary layers much better in that sense. In the actual direction, the grid points are zeros of the Jupiter polynomial, which also leads to more concentration in the poles. And we carefully solve for the absolute pole, we get closer and closer to the pole as increased resolution. So the grid together looks like that, or at least a slice of it, and then you repeat it in all the points will only be very equally spaced. Finally, stable is implemented with by specifying a background entropy gradient, which is at -1 in the areas where you want to allow convection to exist, and then it goes to some high value where you want to suppress convection or you want to stable stratified layer. In terms of a more familiar quantity given the solar frequency, this is how they are related. So given the solar frequency is related to the entropy gradient through all these quantities, thermal expansion coefficient, temperature, gravity, and your control parameters. So wherever you have convection, your n squared goes to negative, so this is -1, and wherever you don't have convection, your n squared is positive. So they can have eternal variables.
So does it also play a role in defining Jordan times?
Um, this one, the convective turnover time scale will be more defined by your thermal gravity.
Finally, so T is still under S. So finally, what is the input? Is that different heading the input finally, or it's really the or in terms of S you define the input period?
Yes, in terms of S.
And from there you can go to the returns, right?
From there, yes, there's a sort of related to resolve for. So there is sort of a
Or is it check whether you satisfy social criteria or not, certain domains, and then certain domains exist, so you have to check that, right?
One question. Like, when you are defining entropy, so you must have some model for the gas or system. Like how you are defining entropy in this?
it's the definition Q by T. And then so you have one gradient that comes in here, and then the entropy contribution is what you saw.
But how is the entropy of the system defined?
It's the heat flux or temperature over in certain case.
So you incorporate a control class system.
But the full derivation is a few pages long.
And that's sort of free parameters, I understand. I mean, it's not very well. In fact, even for the sound, there's a huge confusion on what should be.
Yes, I mean, this program is sort
For
of,
us, I don't know how well it's
and this program is sort of very ad hoc. It just specifies something that has nice.
which achieves what you want to achieve.
Yes, it achieves what you want to achieve.
And in terms of the potential.
So some people, for example, don't do it this way. They instead introduce heat sources in a certain region, which doesn't have
That's the contribution.
So the code I used to simulate this is called Magic. It's free and open source, and it's one of the fastest and elastic codes out there. So would highly advise it. Now, coming to the actual applications of everything I said, the gas giants are sort of very strange in the way it feels. Even though they are both gaseous planets and both are really big, Jupiter has the highest magnitude of magnetic field in the solar system. It's really high, about 1600 microteslas. On the other hand, Saturn has a magnetic field that's comparable with others. Jupiter's field is quite dipolar, but it also has this strange flux patch, which is now been dubbed as the Great Blue Spot, similar to the Great Red Spot, because the paper that came out with these measurements did the rendering in red and blue, and this was in blue, so they decided to call it Great Blue Spot. However, for Saturn, the it is perfectly hyperbola and really well aligned with the rotation axis, which is very weird, especially if you think in terms of Calvin's theorem. This is a perfectly axisymmetric dipole existing out there.
It's not very over period of all the cases.
Yes, the secondary variation on this is extremely low.
So this too, even for the Earth, we know that there are microscopes, where the regions have this strongly localized mounting fields, which are considered boundaries. Is there a common that and that magnetic hotspot you're talking about in Jupiter? Have people looked at that? Or
The idea of this is more that there is probably a random surface. There's some dimension pretty close to the surface going on, which probably gives rise to this. Well, for the Earth, I think it's fluid flows inside the vortex. I mean, for the Earth, we know very precisely where the diamond surface is.
but you don't know the flows.
No, people look at the mini field and the mini vertical views. So the observations are quantified in terms of what's known as the lower spectrum, which I will show in some slides ahead. So I'm just introducing it here. So in the source-free region, beyond the diamond region, the magnetic field can be expressed in terms of gradient scalar potential, which comes out to be this if you solve the Laplace's equation, where you have basically your real and imaginary parts of the spherical harmonics. So you have the associated algebraic polynomials, and you have these coefficients called Gauss coefficients, and then you can write a spectrum of the radial part of the field, and that's what people usually show in magnetic observations of planets in these days. So you have the one for Jupiter here, which is flat in the lower degrees. And you have the one for Saturn, which goes mostly zigzag except for degree 5, which is the bane of our existence, because any perfect diagrammatic field you generate, it usually goes in a perfect zigzag manner because of the symmetry of spherical harmonics. But once this observation result came out, we were very puzzled, and ever since then we've been trying very hard to try to achieve this through simulations. So this is this quantity. You have these coefficients, and then you look at the amplitude squared. So it's similar to a Fourier amplitude spectrum. So you have degree of spherical harmonics and then an estimate of the amount of energy in those degrees.
So specifically, at what scales are the energies distributed across different areas of this source?
And what's very interesting about this is that we know Saturn's field with a breaker surgeon and Earth's field. So we know Earth's field to about 13 minutes, and we know Saturn's field to a greater degree, to 14.
And why is that?
So for the crystal field masks, the internal signal after a little distance. And there's a shameless plug. If you want to generate plots like this or 3D figures like this, you have written a Python package which allows you to play with any planetary magnetic field data.
Although for any magnetic data comes with the model, right? Why should you just be for planetary magnetic fields?
So I've collected,
spherical harmonic code should be.
yes, what I've done is I've collected all the data from different planets in different places. This came up with the teaching tool. I was teaching a class of magnetic fields, and I couldn't find a code that produced any of these images. So I decided to work on it. And so the difference between these two planets seemingly comes from the difference in the interior structures. Jupiter supports the convecting part of this interior, so the animal surface goes to about 85% or 90% of the planet, while for Saturn it's far medium interior, overlain by a big thick stable stratified layer. So the idea is that there isn't much filtering of the field happening here, just a little bit, which makes it just the right amount of dipole, while over here there's a lot of filtering going on, which should make Saturn's field highly dipole.
So when filtering here, filtering will happen both on depending on the scales of the field as well as the time scale of radiation.
Yes.
So they have a same effect. Right? So here you're talking about both kind of filtering or more on depending on the scales,
Small times,
time scales.
but usually the smaller scales can be very faster.
So that's why you can let that will shut out. And the parties, what kind of diameter are those? Where the alpha side, omega, is that known or you can really worry about that too much?
Good question, and yeah, I never thought about it.
Okay.
But at
The
least
reason I asked that is that you need to know that and you can construct similar diameter models.
in the case of
So
terrestrial,
you can estimate the transfer coefficient and compare that with the rotation rate and the difference to rotation.
at least for terrestrial planets, it's typically a square.
People are also writing this alpha omega. So I don't know.
It's hard to get the amount of differential rotation going.
Yeah.
So, case one, Jupiter. Let's say that we get this only prototype somewhere. In this case, we have a 10 integer in this paper, they did a bunch of calculations, and then there's exactly how Jupiter's interior might look like. So they did different quantum mechanical calculations under Jupiter conditions, and to give it one I don't understand what they did, but I know the profiles. So then you profiles with polynomials, and it's fairly easy to plug into magic. So you have density, temperature, gravity, thermal expansion coefficient. This is a weight parameter which is related to the tropic index. And this is the electrical conductivity, which remains fairly constant and then rapidly decays away. This is one of the main reasons why we only simulate till about 99% of the planet, because the last bits are dropping too fast for us to simulate. And once we have done that, we look at where to place the stability stratified. And the idea is to place a stability stratified somewhere around here where the conductivity is just beginning to decay away. It might just have the right amount of filtering. So the first thing we looked at was the effect of what is known as a dilute core. People have been saying that giant planets probably don't have a fixed solid core, but they have something of a more diffuse dilute core. So to do that, what we did was we had a bit of solid core, and then we had a more diffuse part, which we modeled as a stably stratified layer at the bottom. And we don't have a stable layer on the top. And what ends up happening is summarized here. So the black observation, which we are trying to introduce, and no matter what radius of we go to here, all these diamonds become extremely multiple, so nothing matches the observations. So next we looked at, we removed that value part of the core. We went to, we just put a stably stratified layer at the top. And what we find is that the agreement is much better. So the blue one is our best fitting model to observations. And it just fits much better compared to the other ones. It's not perfect yet. But this is a stable layer, 95% of the planet radius, and everything fits very well. Finally, we got a combination where we had code how to particular systems of first and extended version of directly to and what you do is that whether you have our highly stability stratified code here or perfectly solid code, it hardly
Sorry for conducting.
yes. But whether you have stability stratified variant or you have a code which is it doesn't make any difference. They all just become multiple. Even when you put a stable stratified layer at the top, they all tend to become quite multiple.
So can you actually, in any simulations, can you really distinguish between a solid core and a gaseous core which is non-rotating or doesn't have convection? To look the same, right?
Uh,
For the physics perspective.
so that was my idea too when we first started out. I thought it's sort of an inert body that doesn't do much. And it turned out it's actually true. So if you replace the whole thing with a solid core, it's the same thing. In some simulations as well, and Sabina did some simulations for Uranus and Neptune, she observed that some dynamics in this particular can actually
I think overshooting convection.
some convection can lead to some interesting dynamics, but we didn't see any of that in these simulations.
So the turbulence would be quite suppressed in the steady stratified layer, right? So is that why you have this pure molecular diffusivity as opposed to turbulent diffusivity?
Yes. So
That's what one idea is that actually cover your description of how you're describing the interpretation.
and then yes, what is happening is you have very little radial flows, and you have some quite a few zonal flows. But then not really that weak flows.
I mean, if you calculate the correlation function that we got maybe about V dash or V dash, then we should probably figure that out.
Probably, but in general, the flows are very weak compared to the convective flows.
So in calculating simulation, one can actually mimic this with very turbulent, I guess.
Yes, but you would have to somehow suppress radial flows. But finally, the conclusion is that the effect of combination of this also has a line match. So what really matters well is just a stability structure, a really thin stability structure, which extends from just 90 to 95%. And these layers around our best model also matches the pattern of zonal winds on the surface of the Jupiter. It matches it doesn't match perfectly, but you get sort of low zonal winds here and you get a large zonal wind in the equator. Which has been a problem in the past. Without a stable layer, what happens is you suppress all zonal winds. And you won't get one last movement near the equator. But with the presence of a stable layer, we now start to see some zonal winds near the polar regions as well.
What is zonal wind? Is it different from your surface?
So zonal, this means longitude flows
Within
on the surface.
on the surface. So how do you calculate simulation estimation?
So average the longitude and see what the zonal velocity is from different velocities. And then you can calculate it also. So depending for Jupiter, the stability stratified code was a solid code. It's no different from the dynamo. The stability stratified level between 90 to 95% of Jupiter's radius best explains magnetic spectrum as well as zonal winds. And anywhere you try to include extended stability stratified level, you get worse winds. If you want to read on this further, you can read about paper, more down, but on JG reference. So coming to Saturn. In Saturn, we get the 1D profiles from several different sources, which makes it tricky because they are not necessarily thermodynamically consistent because each person is giving us different profile and they're not necessarily talking to each other. So, but in any case, I tried to scrape around for profiles and pick what I could. And after you get the profile, the next question comes where do you put the stability structure? Now, according to this paper, where they look at hydrogen phase diagrams and thermal evolution models, they say that the stability structure should be somewhere here, and the diamond should be somewhere here. The problem is the electrical conductivity starts decaying around 60% of planetary radius. So you're left with very little space for the diamond to operate. So does this work? Well, the simulations are correct. Now the dimension is reduced to 7 per diamond. And the reason is this dynamic region still has some ambiguity that in the secondary diamond starts operating there. So you can see it here. So this shows magnetic field. You have diamond operating inside, you have a secondary that starts to operate here. The left side plot shows spherical round on the y-axis, and this is basically magnetic energy across different radius. So you can see small scale and higher order, and there's quite a bit of energy right here. Inside the state there, it starts getting filtered out, but then you have this single diamond that starts to operate. And despite filtering here and some decay outside to the surface, the dipole still stays very low. For Saturn, you actually want 99% dipole. So this doesn't work, and the surface field doesn't look anything that well. So next, I got in touch with Chris Stankovic, the first author of this paper, and I told him, this is not working. So he said, well, I think you can discard that if you're not interested. That was correct. And he said, well, you should try to look at our new data, and they have these models that look at inputs where they have a still stratified inner boundary, which I treat as inner core, and they have a still stratified there out here. These are still preliminary models, but I tried one, which also needs a tiny place for the dynamo to operate. And this dynamo shell is so thin that it produces a very much dynamo, and you actually look at Saturn like. So you have that operating here, and even after all the filtering and decay, you don't achieve Saturn like that work. So the surface field doesn't look Saturn like. It's highly dynamic, but it's not that which we will want perfect blue in this hemisphere for green here. So to conclude, what we find is that these narrow convection rules of Saturn make it difficult to obtain a stable dipole field. So there's a mismatch between what we find from the simulations and what is inferred from the geostructures, about the geostructures inferred from other methods like phase diagram and cosmology. And so, I tried to convince the planetary community to produce a similar, fully consistent interior property profiles, which ultimately will be thermodynamically consistent. Now, this is the last piece. Just one of 3 solar masses simulating construct. So this is the EG stream. EG stream that we are starting with some of the EG stream of Stephens. And together we simulated 3 solar masses during the construct. The profiles for these were obtained from NISA, Stable Evolution Code, and we only simulated 50% of these parameters. After that, the density is is too high. We're trying to go up further than maybe 70-80%. And we get profiles, density, temperature, gravity, and so on. And once we fit that, we start on some simulation, and I have some nice movies today. Let's see this. So this shows radial quaternion slices of radial. So radial was doing radial inverse. And we start with random noise, and slowly convection will be matched. So this is the convective zone inside, and outside is the radiative zone. And we start seeing gravity waves propagating. So now convection has started, and you can see nice gravity waves propagating in the radiative zone. The next movie will show the zonal or longitudinal flow and the axisymmetric part of it. So this is a measure of angular momentum, just the axisymmetric part of the zonal flow. And initially you have with random noise, so you have nothing. And towards the very end, after the boring part, you start seeing formation of convective columns in the center, and you start seeing zone flows developing here. So there is angular momentum that the outer part of the fluid is in. So this was towards the beginning of the simulation, and now once the simulation is saturated, you still see that there is angular momentum increasing here. So this rate will start to keep it more deeper. So you can start seeing more and more modules getting integrated.
So are those what they call it cells?
I don't think these are quite common cells. If you take first question, actually, I don't think these
Are these cells to access information?
yeah.
How normally the structures? Yes, the ones that you said.
Yes. And then just stressing 3D visualizations. So this is the boundary between the convective and radiative zones. So inside you have convection going on. The hypersaturated colors are to bring out the dynamics of the radiative zone. And you can see wave light radiations everywhere in the radiative zone. And nice convection columns. In terms of angular momentum, it's hard to see, but if you go over here, you'll see over time the angular momentum actually keeps increasing in the outer parts of the brain. So there is a angular momentum transfer from the core towards the envelope. That's fine. Whether it's high enough to explain observations, we don't yet know. These are still we did the simulation, did some preliminary analysis. We haven't really gone into deeper investigations. So what we find is that computer force in the interface that we drives to internal gravity waves. In these ways, to transfer the angular momentum. But the effect mechanism of radiation and 5 mm transfer we still haven't investigated. So to summarize, we'll say Finnish stratified layers and give rise to a host of numerical and MHD phenomena. In fact, they can filter out the fields, and the stars might be able to transport energy through the generating waves. And I think there's a lot of potential work in looking at stable stratified layers, also from the dynamics point of view, and especially the combined efforts of stable layers and magnetic fields. There's our group is called talking this called MACFI, stands for magnetism and planetary interiors, and we actually have MACFI as a symbol. So there's my email. You can follow me on Twitter. I'm happy to take any questions.
Actually, I had no that before yesterday. And we're going to be friends for a couple of months. I like the nice stuff that he puts out with the videos and stuff. That's how we started communicating. For all of you who are doing research for my home.
So, you're talking about waves. So, what's the time scale of those waves?
That's a good question. That's something you should look at and get looked at that. I mean, we can eyeball it very fast, but to actually quantify it, I would have to do a Boolean analysis of it. Typically, and look at what is with respect to the rotation. So, short answer is no.
So, do these waves get transported from the surface to the atmosphere as well?
That's a good question. Depends on how the atmosphere is, but typically they should. And depending on the density there, the wavelength that it is.
Is he talking? This is Jupiter? No, this is C master.
3 master.
Yeah. So it really depends also on class of region. If you expect a big drop within a surface.
I mean, these are fully hydrodynamic simulations. There's no.
Right. So I would not be skeptical to thinking that this waves would naturally get propagated to the atmosphere.
So, they must dissipate somewhere. Like,
They can even project back, just like the crab is at the start. This happens in the sun.
So the idea for what you mentioned, that they can self-interact and sort of once their amplitude becomes too much, they can give rise to sort of start to give rise to some influence, and then the dissipation of this.
So you, I mean, I'll just ask you to ask, well, finish.
So I have a big technical question related to how magic defines the flow field or magnetic field. Now, tell us define it in terms of purely radial potential. If I'm not wrong. You take a purely radial potential and you take curl of it once or twice and then curl once.
But like really, really is what.
Yeah, I guess you will see there along radius.
There are functions of all three.
Yes. So, there are works which define these three dimensional components in terms of azimuthal scalar potential. Okay. Azimuthal potential. Here you are bound to do twice, derivative twice, where you could do derivative once and you could get the whole 3D profile. We expect more transmission here in this discussion are bound to define these fields like these and these linears with a structural code.
No, you cannot find the in terms of analyze certain components.
Or you start from theta and phi controls in magic.
No, here we always go with the radial part and go with the radial part.
In magic, typically they prescribe the regular component and they project it.
Yeah, I've never seen in terms of another.
Is it a relation? Because magic is a structural code. Is there any scope to define the relation?
There should be like you do it in terms of certain amounts that we see usually. There's usually one is radial, one is gradient of the radial part, one is square of the radial part.
So then what is green taking curl box, and that's how you introduce some transition error to every dehydration process.
But the radial is spectral space. Yeah, I don't know that.
Yes, the advantage of remote perspective. Other perspective. Also, this is much faster.
It doesn't have chip.
But magic can do also find a different.
Oh,
The question I was going to ask is, I mean, just like the sun, you have this, you look at oscillations on the surface, right, and then figure out what's going on in the Jesus right? Something similar that we do for gas giants.
Yes, people are actually trying it right now. One for Saturn, there's a ring assessment where you look at oscillation of the secondary rings, and then you can figure out what the gene was inside the because the gravity is working in oscillation. So that's what Chris Mankiewicz doing ring seismology figuring out how to do those. And more recently, Dave Stevenson and one of his students at MIT, not helios seismology, gas giant seismology. And they look at something similar to the Kaplan things in the star. They look at the luminosity of Jupiter changes over time.
So, I mean, there's also a stably stratified layer of the sun, which is just below the ground.
Fill the dimension
This is not very well understood on the ocean layer. It also coincides with aeroplane, which is strong shear evolution. Have you ever put in that layer?
No, never looked at sort of bottom status rate. I mean, I looked at in terms of Jupiter where it doesn't do much, but not in terms, not as an application of the sun. I should be fairly
There's this theory that there's any field in the sun, which is negative. And conducting is not used. It's stable conversion has chosen materials. But then you have like what you sort of are seeing for example, if you have a stable state that and the condition is good, how would that figure out what's hidden in the interior and put out into the conversation? And how does that interact with the data? It would be a very interesting to study if you would done this for us. So,
I mean,
its ideas tend to be looking at Saturn.
and it depends how fast the field is varying. Let's
So
say
it doesn't vary in the interior, or it's up in the convention of the universe, I even place the critical types, even if it's not. That would be very good. But that would require like solar cycle times with simulations.
yes.
Maybe over a long time period because we're looking at fields diffusing out in the interior. Particular molecular tissue, that's not like it. It's not because it's not time, right? So I don't even know if it's possible to do this. You might be able to do it. Rajesh is here. It is like, so here, like, access to like 50,000 codes, 100 codes, unbelievable. We have access to like 400 codes. It's like 2 hours of math difference. So what he can do, what we can do. There's a computing power. Any more questions? Yeah, go ahead.
Questions collectively. Are there no data from the atmospheric perturbation? Let's say how much cases of that?
So it gives you the possibility that the density becomes smaller. Because I mean, we don't expect it to do much because the density is so low. And also we can't see it.
The energy density from those regions is also quite significant. So even though the particle density is very small, but the energy density is significant.
I mean, it's possible that problem that we just can't simulate it. So what some people have done is they have, for example, simulated a very thin layer made of helium, and then just simulated that thin atmosphere to see what kind of effect that might have. And what people typically try to do in terms of gas turbines is the Saturn picture. They try to achieve this exactly. And you can, so some people, for example, Rakesh Chandra does some simulations where he does it in the other ways, or pseudometers,